Fantastic. Ross, over to you.
Great. Okay, thanks very much, John. So yes, I am Ross Potter. I'm currently a data scientist at Clarivate. I'm also a visiting scientist at Brown University. I was previously a postdoc there under Jim Head. And while being a data scientist is my current day job, I'm still doing sort of research on the side. And today I'm going to talk about something I did at the NASA Frontier Development Lab a couple of summers ago. But before we get into that, I just want to briefly talk about Clarivate. So if anyone has ever used the Web of Science, that is a Clarivate, well, that's owned by Clarivate, and they own lots of other sort of attachments and things for sort of academia and universities. So I just want to briefly describe two that may be of particular interest to researchers, which are Copernio and Publons. So Publons is yet another academic profile that you can have online, where you can list all of your publications. If you have ORCID IDs, you can link that up as well, so that can import all of your various publications. But the main advantage over Publons is that it can also track all of your reviews that you've done. So sometimes when you review a paper, there might be a link directly in the review to say if you want to post this to Publons, or you can email Publons the review verification from the publisher. So this is a good way of being able to track all your various reviews that you've done, rather than just keeping them in a Word file, which is what I've been doing previously. So it's free to sign up for, so that's very useful, yeah, if you want to sort of keep track of all your various reviews. And then also Copernio, which allows you to quickly access research papers. So rather instead of going through lots and lots of different Google searches, different web pages trying to find a research paper, with Copernio, you can have a plug into your browser where you can instantly access the PDFs of papers. So Copernio you log in via your various institutional emails. It also searches through all of the open access articles. So you're able to access journals with just one click rather than wasting 20, maybe 30 minutes trying to find a paper. So yeah, that's very useful as well for finding papers, and that's free to add in your browser. So if you're looking at research papers a lot, it's one thing to consider adding as a plugin. Okay, so I'll now briefly talk about the NASA Frontier Development Lab as a program itself before I get into the specific project that I worked on. So the NASA FDL, Frontier Development Lab, has been going for about 4 or 5 years now, and it's billed as artificial intelligence research for space exploration and humankind. But artificial intelligence is a bit of a broad, vague term. So really it's using machine learning. So can we take a lot of data, can we put those through various algorithms, and how can we use this in collaboration between research scientists and commercial partners to help NASA move forward in their exploration. So the NASA Frontier Development Lab took place in the Silicon Valley area of Northern California, specifically in Mountain View at the NASA Ames Research Center, and also at the SETI Institute. So it was very nice to spend a summer in that area of California. So this is just a few pictures of the Ames Research Park where we were based. And the program itself consisted of 9 different teams. There were 37 of us different researchers and 50 mentors. And the program itself was open to people at different educational levels. We had undergraduates, PhD students, postdocs, and also various people who work in different industries, specifically machine learning engineers. So it was a real mix of professions, ages, and experience. The program itself lasted 8 weeks, and we basically came up with the ideas during the program itself. So really only spent about 3 to 4 weeks working on our actual projects. So we spent time sort of coming up with those ideas. And at the end of the program, we delivered our results to some NASA program managers at the Ames Research Center. And we also had a final presentation at the Intel headquarters in Mountain View to present to the general public as well. So that was very interesting. And the program itself was split into 5 different areas. Now these change year on year. So I'll just briefly describe the different areas that were looked in my specific year. So the first area was Earth observation, and this was based in the FDL program in Europe. So as well as running the program in the US and California, they also have a European-based program. So that was based on Earth observation, looking at 2 specific challenges: disaster relief and informal settlements. So this would be using satellite data to look at the effects of natural disasters, for example, floods or hurricanes, and informal settlements in terms of displaced peoples, either because of looking at informal settlements being developed. This could be because, again, of natural disasters, or maybe because of civil activities in a country. The rest of the programs were based in the FDL at California, and the first was astrobiology. And so again, there were 2 challenges here, looking at trying to understand what is universally possible for life. So they were looking at using machine learning to look at the chemistry of different biospheres and looking for ecological signals to try and see what they could tell us about what could, if they could represent life. The next set of challenges were looking at space weather. So some of these were using data from real time instruments. So they were using data from the Solar Dynamics Observatory and specifically the Atmospheric Imaging Assembly to predict solar spectral irradiance. And this was relevant for specifically the effect of irradiance on Earth, particularly in the upper atmosphere, and to also improve ionospheric models using GNSS and GPS data. Again, to see the effects of irradiance on interfering with signals with those specific satellites. There's also an exoplanets focus. So again, this was using information from the Transiting Exoplanet Survey Satellite, or TESS. And now previously, data from this satellite had been manually curated about every month. So with this project, what they wanted to do was increase the efficiency and efficacy within that data to be able to better predict and detect exoplanets. So to generally speed up and decrease the amount of manual labor required to sift through the data. And then the final group of challenges were based around space resources, and these are particularly focused on the moon, and this included the project that I was involved with. So the first challenge was looking at robot swarms to try and use a group of robots in collaboration with each other, try and work out navigation paths and best places to go and travel, and to work amongst themselves to work out the best routes and objectives. And the second challenge, which was the one I was involved in, and we'll talk about more in detail in a few more slides, was looking at rover localization, specifically tying this together using orbital maps with surface perspective imagery. So with all of the various projects, we also had commercial partners. So for these space resources projects, they're shown on the right here. So we had help from Intel, Space Resources Luxembourg, and XPRIZE. So they helped us provide us with computational equipment and abilities, and also various of their own employees to help us with all the various machine learning help. Each of the FDL teams consisted of 4 researchers and then a few different mentors. So our team consisted of 4 of us. So me and Ben were on the team as these sort of subject matter experts, as we're specifically looking at the moon and sort of lunar research. So Ben's background, he was an astrophysicist. And then we also had Philip and Andrew, who came from a more machine learning background. So they were the more machine learning experts on the team. So Phil is currently doing a PhD looking specifically at this particular topic of rover navigation. And Andy works as a machine learning engineer for Audi. So we had a good mix of experience in terms of what we needed from the science side and also from the more applied machine learning side. And this was true of all the different teams. So while we're there, we also got to look more around NASA Ames. So we got to see their supercomputing center, that's in the top left. The bottom left, they also have one of the world's largest wind tunnels there, and a few other of the various equipment they have on the Ames campus. And as I mentioned previously, we also had a final event at the Intel headquarters where we presented our work to the general public. We also had a 3D headset to see if people could themselves locate where they were, as well as our own algorithms. So that was good to get people a more idea of how difficult a process this is for a human to do, and why machine learning algorithms are useful for this process. The program wasn't just about carrying out the projects, but also for about getting outputs that could be used, going out into the academic community and also into the commercial side. So they've come out of this with different publications. So you can see here, this includes Science Advances and their Astrophysical Journal letters. So this has had quite a big impact as well in terms of having results that are publishable and are being used in future research. And our particular work was presented at the International Conference on Intelligent Robots and Systems. And this is also available on the IEEE Explore website if anyone has access there. I can also provide a PDF copy if anyone is interested in reading any more about this topic. So just a few notes about the Frontier Development Lab. So if you go to frontierdevelopmentlab.org, you can find out more about the program. As I mentioned, they also have a European version of the program as well, and that's fdleurope.org. The program runs from mid-June to mid-August, and even with the COVID situation this summer, they were able to run it virtually. So even though it wasn't ideal, they were still able to have the program run. And the application process was very straightforward. The only bit that required more sort of input and imagination was thinking of a short question about why you want to be part of the team and what you bring as a researcher, and why your interests are relevant to the proposed tasks. Okay, so that was a bit about the program itself. So now I'll talk about our specific project, which was rover localization. So why is localization important? Well, it's important for 2 main reasons, and these are navigation. You want to know where you are and how you can get to where you want to be. Especially when you're kind of on the moon, you don't want to suddenly fall into a crater or get to a base of a hill and not be able to go anywhere. And it's also relevant for your various objectives. If you want to sample a particular material, you want to make sure that you're on that particular material or rock, and you're collecting what you think you're collecting. So localization for humans we're quite good at that. So for example, if I just showed you the image of this particular image, you'd probably know where you were, just from the various buildings and skylines. Similarly, with this image, you'd probably be able to pick out where you are. But when we don't have such visual clues, it can be harder. So we can also have access now on our phones to be able to tell us exactly where we are, pinpointing our location, and tell us exactly what everything else is around us. And even if we're out in the deepest woods, we may not have access to GPS satellites necessarily, but humans are still very good and adaptable in these situations. So with a map and compass, you can normally do pretty well in terms of knowing exactly where you are and how to get to your preferred location and achieve your objectives. But when you're confronted with a picture in front of you like this on the moon, there's not really much to help you sort of pick out any particular features that would help you locate where you are. So this looks a pretty flat surface. There are a few rocks, maybe a few hills in the distance and a crater. But apart from that, this could really be anywhere on the moon. And similarly, if you are on Mars, you maybe see a slightly more variety of features here. But again, the landscape would look very similar, probably no matter where you are. So it'd be very difficult to be able to pinpoint exactly where you are in terms of your location. And unfortunately, we don't have any GPS system around the moon or any other planet. So we can't rely on that to be able to help us pinpoint our location. So we have to use other methods to be able to locate where we are. And even, so this problem isn't solved particularly well even at the moment. So there are various different methods that you can use to locate yourself on the planetary body. So this is a figure from a paper that was looking at the U2 Chinese rover on the lunar surface. And the three colored lines here, the green, red, and blue, are showing different paths of the rover calculated by different methods. So for example, the green line is by dead reckoning. So this is basically measuring how many times the wheel is turning, looking at the distance it's traveled, and trying to work out how far it's been and where it's gone. The blue line is looking at digital orthographic mapping, so looking at different images and trying to figure out where the rover is. But as you can see, even with these different methods, they all give different results. So it's still not entirely clear sort of specifically where the rover is. And obviously this is very important, again, as I mentioned, if you're looking for sample collection. So with that sort of background, our task was then to come up with a way to use surface perspective to satellite perspective image matching by machine learning to improve this localization. And the goals here were to improve localization accuracy over the current methods, to offer greater automation and faster calculations, and also to produce a benchmark dataset that can be used for various localization purposes. Okay, so a quick summary just of machine learning. So machine learning is essentially you're making predictions on based on some kind of data. So you want to build a predictive model using part of that data. You want to be able to test that model on another part of the data. And you want to be able to tweak the model if the predictions aren't good to improve its accuracy. And then when you think you have a good model in terms of its predictions, then you can implement your model on a new set of data, and hopefully you will end up with some good results. And depending on your specific problem, there are various different methods of machine learning you can use. So linear regression is actually a type of machine learning. So that's specifically supervised, where you know what your output is. You're just trying to create even a simple XY relationship. You can have data where you don't really know if there's any relationship. So you want to kind of cluster data together. So that would be unsupervised, where you don't know what the result necessarily is. And you also have artificial neural networks for more data intensive projects, so specifically images and text. So we are focusing on images. We'll be using convolutional neural networks, which I'll explain a bit about later on. As I mentioned, we're trying to use surface images and satellite images to match these up to try and help us localize where we are on the surface of a planet, so specifically the moon. And thanks to the Lunar Reconnaissance Orbiter camera, we have lots of very high resolution images of the lunar surface. So these have resolutions of up to 50 centimeters per pixel. However, images from the surface of the moon like this aren't actually that common. I'm not sure of the exact number, but maybe just a few thousand, compared to the satellite imagery, which is in the range of millions. And this is a problem because to be able to create a specific data set for a machine learning model, you need lots and lots of images, not only from the surface perspective, but also from the satellite perspective. So because of the lack of images from the surface, we had to create our own virtual moon environment. So we did this using a lunar landscape which we purchased and did the modeling using the Unreal Engine. So this is actually a gaming engine that you can buy and create your own games within that. But this was the best package we had available to be able to instantly create a virtual lunar environment where we could quickly create lots of both surface and satellite images. So in the end, we ended up with about 10 terabytes of data for images, and that equated to around 2.4 million images, which were created from our data set. And again, this high number was required due to the machine learning algorithms, which require many millions of images to be able to pick out the necessary features and to be able to make good predictions when it's given a new image. So how did we go about sort of using these surface and satellite images? Well, first of all, we have to pretend that we're a rover on our virtual moon surface. So first of all, we want to know where we are. So we might take a picture straight in front of us, to the right of us, behind us, and to the left of us. So we now have a 360-degree view of the surface around us. And what we want to do is to be able to turn this into a top-down satellite image, which then can be matched with, for example, the satellite images we have from the LROC data. So what we did, we used some OpenCV orthographic libraries to then convert these 4 images into an estimated top-down view. So this is what's seen here. Now this looks slightly odd, and this is because the algorithm or when you're inverting it or changing an image to a virtual view, it can only look so far into the distance, and it can't look over objects. So if there's a large mountain in the background, it doesn't know what is beyond that mountain, so it just assumes that it's a flat surface. But we'll see when we get to the algorithms that they are able to take this into account. Okay, so this will be a short video. So the top screens are showing again those 4 different views from the rover on the surface. The left bottom image is showing that reprojected view, and the image on the right is showing the true orbital view. So what you would see from space. So we can see how this changes as we sort of move across our landscape. So again, we can see that the reprojected view doesn't quite match the orbital view. We can see that there's, again, when there comes across any kind of rock or elevated surface, the reprojected view cannot see kind of beyond that. So we see these kind of strange distortions in the reprojected view. So one thing we want to do with our machine learning algorithm is to make it pick out the features in this reprojected view and match it to true orbital view to be able to give the best impression of the data and to learn how these reprojected views, how they truly compare to the true orbital images. Okay, so to look at our various data, we wanted to test our algorithm, so we had to pick out a training area and a testing area. So from our virtual moon, we picked an area 2 kilometers by 2 kilometers, which contained 600,000 images to train our algorithm on. We then validated it, so tweaked the various models on 140,000 images, and then tested it on another area, which also contained another 140,000 images. So the algorithm we used, as I mentioned, was a convolutional neural network. So to train the specific network, we used this approach. So we gave the neural network a true orbital image and the reprojected image. And we wanted the algorithm to be able to learn the associations between what it sees in the reprojection and the true orbital images. So we provided it with 50% data where the true image and the reprojection were the same area, so they matched, and then 50% where the images did not match. So it was able to distinguish between those features that did help recognize a true region and those that showed that regions were different. So the way the algorithm worked, so we used a residual network, which is established convolutional neural network with 50 different layers. So what this essentially did was take all of the parts of the different images, concatenated that down into a single feature vector, and then went through a neural network which learns the various features within the images to then get it to understand what features were similar or different between whether the images matched or didn't match. So the neural network, to begin with, would pick out features like whether areas were particularly light or dark. It would then look at areas where there were maybe lines or sort of circles, so specific features, and then work it up to then building those up into sort of bigger objects. So for example, craters or rocks. And then after we trained our network, we wanted to implement it. And for this, we gave it, again, a true orbital image and a reprojected image. And we got the algorithm to tell us whether the two matched. And this was based on looking at a similarity, the differences between various parts of the images to see how much of a match or not match the two images were. Okay, so that's explained in a bit more detail here. So on the left, we have an aerial reprojection. So this is a true satellite image of a particular area. And this area is located within the satellite map on the right. So it is in fact located in this green box here. So this is the true location of this reprojected image. So what we want to then look at is to, once we're given an image within the satellite map on the right, we want it to be able to see if it can best locate this area based on the reprojected image that the rover would have created on the surface. So the algorithm would then go through each different square within our region and then run the algorithm on each of these specific images. And it would then assign a likelihood of whether the image matched or didn't match to our reprojected aerial image. So as you can see, the different areas within this particular area can vary quite a lot. Some of them look very similar. So we wanted the algorithm to be able to pick out what areas best matched our reprojected image. Okay, so again, the green box is showing where the true area is of this area reprojection. And the blue boxes that are coming up in the next few slides will show the algorithm's best guess as to where this location is. So that's our first location guess, our second, our third, our fourth is a bit further out, and our fifth. So this is showing that the algorithm is, while not specifically picking out the area entirely, it is picking up enough information to be able to at least narrow down the search area of where this particular location is. So we can see that it's focused in on a specific area, so you can discount a large percentage of the rest of this area and concentrate on around the areas, around the blue squares. This figure is showing the performance of the algorithm. So the x-axis is saying the minimum distance from the true location. And if we just look at the dotted pink and purple lines, we see that on the pink line, so the 10% of the recommendations that the algorithm suggests were within 5% of the true location. And the top, within 10% were the top 5% of recommendations. And is also comparing it to a few other standard sort of image classification matching. So SAD is a sum of absolute differences, and SSD is the sum of squared differences in terms of just locations of specific pixels within the images. So this is showing that the algorithm produces fairly good results. This is able to generate these results in a matter of seconds. But most importantly, it's able to reduce the search space by about 90%. And this will help any then manual processing in terms of specifically locating where the rover could be. So in summary, our project was to use surface perspective to satellite perspective image matching via machine learning to try and better locate rovers on the surface of a planet. And this is important for not only for navigation purposes, but also for objectives to making sure you'll be able to sample any material that you want to do correctly. So to do this, we built a convolutional neural network. So this was on top of the residual net model to be able to process the images. The results will be able to generate it in seconds. And again, we're able to decrease the search area by around 90%, which will help any human in the loop localization, specifically for pinpointing where the rover could be. With all the data that we created, which was about 10 terabytes altogether, we created a public data set that can be used for various localization purposes to try out people's own algorithms, and also that we can use to improve our own. And just to note that this work will also be presented virtually at the International Symposium on Artificial Intelligence, Robotics and Automation in Space. If anyone is signed up to do that, then they will be able to see a summary of this work there. And to look at our public data set, you can go to moonbench.space. You can see all of our various data there and play around with the data set yourself to see if you can come up with any new algorithms or better localization than we managed. And just as a coda to our project, we had also planned to do some real-world localization here on Earth. So we were working with one of the scientists at SETI, Pascal Lee, who does a lot of work in environments that are comparable to Mars and Moon, so specifically in the Canadian Arctic. And he was going to Devon Island up in the high Arctic in Canada to do some field work. And what we wanted to do was to put on some cameras and some GPS tracking material onto their various Humvees that they were using to get around to get a real world data set of our images from the ground, and then to match these with Earth satellite images to have another data set to be able to work with. Unfortunately, the weather was particularly bad that summer. Their Humvees only got about 50 or so meters, and then they couldn't travel anymore. So unfortunately, we didn't get any data on that particular field trip. But this is something that would be very useful in the future to be able to also compare and benchmark other data sets against. to have some real Earth-based observations. Okay, this is my final slide. So yeah, just again, a reminder about the Frontier Development Lab. So if you're interested, please go to the website, or you're free to email me any questions about that. The program runs from mid-June to mid-August, and that should be running again next year. And then if you are interested in the Publons profile, so you can manage all of your reviews, you can go to publons.com. And if you're interested in getting the Copernio plugin to be able to easily access PDFs, you can go to copernio.com. And I should also mention that as research is sort of my side hobby at the moment, but I'm still sort of trying to keep that active. So my research has been in using a lot of the ISAIL shock physics code that was also presented last time. So I'm also interested in potential collaborations using any ISAIL modeling or any cratering. So if you are interested, please email me, and we can take any discussions further. Okay, thank you very much.